And so we're going to change up the pace just a little bit today. We're still going to talk about circles a little bit later in the lesson today as well. But in this case, we're also going to add kites and rhombus to our area formula. We talked about area of a circle last week. We also talked about the circumference of a circle. We talked about the area of a sector. And we talked about the circumference and the length of a circle, length of an arc. Today, we're going to, first of all, talk about the rhombus and the kite formula. Find the area of it. Okay, and here's the one thing I've seen a little bit is we're having a hard time remembering the difference between perimeter versus area. Okay, when we talk about a circle, when we go around the outside of the circle, we call that the circumference. It's the same as the perimeter of a polygon, right? We talked about perimeter a lot early in the year. Now we're adding circles to it. But if we talk about perimeter or circumference, we're talking about going around the outside. If we talk about area, we're talking about trying to fill in the figure with something. We talked about like laying carpet down on a floor, okay? How much area would it take to cover? Okay, if I was going to do grass seed on my lawn, I would want to know how much area do I have, or how much area do I need to cover in order for me to buy the right amount of seed or fertilizer or whatever I'm going to do for my lawn. So there's definitely applications there of where you could see this being used. We don't see shapes of things in rhombuses and kites very often, but if we wanted to find the area of these two figures, these two have the same formula. Area equals 1/2 times D1 times D2. D1 and D2 are the diagonals. So it's not even talking about the length of the sides. When we find the area of a triangle, we're going to do base times height divided by 2. When I find the area of a rectangle, I take base times height or length times width. When I do a rhombus or a kite, I'm using the diagonals to find the area. So the diagonals are the length across the inside. Okay, and here, it doesn't really matter which one is which here, because when you multiply 8 times 6 or 6 times 8, guess what? We get the same number, right? And so my formula here would just be 1/2 times 8 times 6. So the math is pretty straightforward. Okay? You do not have to distribute it. There's no plus or minuses there. We're just multiplying all three numbers together. Okay. So you could do it a couple of different ways. You could do 8 times 6 and then take half of it. You could do half of 8 and then multiply it by 6. But it is not a distributive type problem like we've seen sometimes. Okay, this one here, not really any different. Doesn't matter which one you label as D1 and which one you label as D2. If I labeled 10 as D1 and 7 as D2, then that would be perfectly fine as well. Those are my two diagonals though. So 1/2 times 7 times 10, and then that would be 35 centimeters squared. Not too bad if they give me a picture. If they don't give me a picture, but they just straight out give me the two diagonals, pretty simple, right? All we got to do is plug that information into my formula. You don't really even need a picture. 1/2 times 4 times 5. All of these are area, so they're all feet squared, centimeters squared, inches squared, whatever unit we're talking about. It's always squared. Okay, this one here, they don't just come right out and give me the length of the diagonal, but it's pretty easy to come up with it. Kind of like they did at the very beginning. We want the length of this whole thing, which is 8 plus 8. And then we want the length of this whole one also, which is 15 plus 3, which is 18. Okay, just the length of that whole segment. We don't have anything about the outside or the sides of the kite. We don't really need the sides of the kite to find the area. Probably the thing that gets left off the most here is the 1/2. We forget to multiply by 1/2 or divide by 2. So we're just going to take half times 18 times 16. There is no label here, so what we're going to do is just use a generic label of units, and I just use units squared, because we don't know if it's feet or centimeters or whatever, so we're just going to leave it alone. Show you, and I think even on big ideas you might have a situation where in a kite and in a rhombus the diagonals are perpendicular. So if I gave you this as 8 and I gave you this as 12 or whatever it would be, then I could find a piece. So are we going to use the Pythagorean theorem today? There's a good chance, right? And that's the one I told you. We're going to continue to see the Pythagorean theorem. Okay, we got a little bit of vocab here. Okay, this is another type of figure, another type of polygon. A polygon is anything that has sides to it, right? So a circle is not a polygon. And you might say, well, why are they drawing the circle around the outside here? We'll talk about that here in just a second. But first of all, we've actually seen this word before, regular. What does it mean for a polygon to be regular?
Standardized.
Okay, which tells me what?
All the sides and angles are equal to.
Okay. All sides and angles are congruent. Okay, sometimes it'll just come right out and say all of the sides and angles are congruent. It may be marked on the picture, or if it just uses the word regular, we already know that to be true. Okay, so figures that we know are regular would be an equilateral triangle. It has 3 equal sides, and all the angles would be 60 degrees. A square would be a regular quadrilateral. You have 4 sides, all 4 sides are equal, all 4 angles are equal. We talked about this one early on in the year, an octagon. A regular octagon is like a stop sign. It has 8 sides, all the sides and angles of that stop sign happen to be the same length, same measure. Okay, so those are just some examples of regular polygons that we see all the time. Okay, first up here is an apothem. Okay, an apothem is this blue line right in here. Okay, the apothem is PQ. An apothem, and I'm just going to kind of write this out so we know what the apothem is. Okay, kind of a weird word. I know it's a new word for you. An apothem connects the center to the middle of a side. Okay, so right here, MN is a side of that polygon, right? I'm going to connect the center, and what it's going to do is 2 things. It's going to be perpendicular to it. We can see that here because it's a 90-degree angle. It's also going to bisect it. So it's the perpendicular bisector to that side. And so you might even write that it is the perpendicular bisector to that side. That's what we call the apothem. Hey, here's where the circle comes into play. If I have a regular polygon, this one's a 6-sided figure. If I start right here at N and I go around the outside of that figure and stop at N again, okay, I can make a circle, right? And each time along the way, I'm hitting a point on that hexagon, on that polygon, okay? And so we call this a circumscribed circle because it goes around the outside of the polygon. PN is the radius of the circle. It's also the radius of the polygon, okay? Because PN goes from the center to the edge of the circle. It also goes from the center to the edge of the polygon, okay? So your radius is going to connect the center to a vertice. Any vertice, okay? I could go like right here. That would be a radius, okay? And I could connect P to any of those points. You got 6 different points. I could connect P to. All of those would be radii. So you have 6 different radii I could draw in. You also have 6 different apophthegms I could draw in. I could draw an apophthem here. I could draw an apophthem here. All of the apophthegms and all of the radii are the same length in that one particular figure. You just happen to have 6 of them here. If I have a hexagon, here I have a 6-sided figure. If I have a 6-sided figure, that means I have 6 radii and I have 6 apophthegms I could draw in. You're not going to have to draw all of them in there. But just to know that they might be drawn in different places within that figure. Okay, MPN. MPN is this angle right here. Okay, it starts at M to P to N. That's what we call a central angle, because the center of that angle is at the center of the circle or the polygon. I could also say MPQ. I could say QPN. There's a lot of different central angles there I could name off. Okay, the most important thing is that P must be in the middle, because P is the center of the circle. It's also the center of the polygon. So it's got to be the center of my angle. Okay? And I can't just call it angle P, because there's all kinds of angle P's in that picture I could draw in. I could call this one a central angle as well. I don't have a letter down here, so naming it I'd have to put another letter in there to name that. Okay, one of the things that we're going to do today, in 11.3, we're spending 2 days on it. So what we do today is going to kind of lead into what we do tomorrow. Today we're going to be trying to find measures of different angles that they give us. And so the really important part is we got to pay attention to the order of the letters here. Okay, so if I have AFB, follow the path of the letters, just like we've done all year long. I'm going to start at A, I'm going to go to F, and I'm going to finish at B. So I'm going to go A, F to B, right? And so when I go A, F, B, we're talking about that one right there, that big angle, okay? We can't really just tell by looking at it. And so we have a way that we're going to be able to do this. So I'm going to draw a picture over here. Of this figure, okay? If I were to draw in, right now this is a 5-sided figure. If I were to draw in all 5 radii, what do you think would be true about all the 5 central angles that I have? What'd you say, Ryan? They're equal. Yep, absolutely. They're all equal, right? I have 5 central angles. All 5 central angles are going to be congruent. And not only are they all congruent, what does this form on the inside? Circle. If I put those 5 angles together, it makes a circle, right? You kind of see it all there together. And so to find angle AFB, I'm going to take 360 divided by 5. So if I have a 5-sided figure, I would divide by 5. If I had a 6-sided figure, I would divide by 6. And so the number of sides tells me how many different angles I would have. 360 divided by 5 is 72. So each one of these central angles is 72 degrees. Okay, the next thing I'm going to do is I'm going to redraw this big triangle in the picture. So this is BFA. I'm labeling it so you know which triangle we're talking about. It also has G. GF is the apothem. And what I told you about the apothem is that it's the perpendicular bisector to the side. So I know that it makes a 90-degree angle down here. And I know it splits it in half. Okay? Now, we talked about something like this early on in the year. If this is the perpendicular bisector, then what do you think would be true about these 2 angles right here? what happens to angle F? Anybody think they got an idea what would happen to angle F here? What do you think, Ryan? Cut in half, yeah. GF is going to split this angle in half. Just a second ago, we said that this whole angle was 72, right? So what that tells me is this is 36, and this is 36. 72 divided by 2. So angle AFG is 36 degrees. Just got to pay attention to the path of the letters, right? It's 72 cut in half. GAF. GAF. If I covered up this half of the triangle, I got a right triangle on this other half, right? How many degrees are there in a triangle? 180, right? And we know this guy down here is 90. We know this is 36. So what I could do is I could take 180 minus 90 minus 36. And that would leave us 54 degrees. Okay. So we're using a lot of different tools and different theorems and properties that we've used early on in the year, like perpendicular bisectors, 180 degrees in a triangle, things like that, that we've kind of seen pop up at different times throughout the year. Okay, this one here, we basically kind of have the same basic idea. Thank you. The first question here on the left, it wants to know a couple of different things, okay? We're going to find all 4 of these. So it's not a multiple choice question. We're going to find all 4 of these answers, okay? First of all, the radius. The radius is going to connect the center. The center is F. F to which segment? Which one of those segments would be a radius? There's a couple of them. Okay. FC would be one. Okay. Do we know the length of FC? Nope, it's not labeled, right? FE, right? E is a vertex, right? Do we know the length of FE? Yeah. Okay. So what's the length of the radius? 6.8. Okay. There's not really any work involved there. You just have to realize that any of those, all of them are the radius, right? Any of those could give me the answer there. AF, what would we call AF? The radius, right? Because it connects F to A. A is a vertex. So guess what? It's the same thing. It's also a radius, so it's also 6.8. If I know one radius, I know them all. And so that's the good news. Okay, the apothem connects the center to the middle of a side. The one that I have drawn in here, the only one that I've drawn in, even though I would have 5 of them, the one that's drawn in here is this guy right here, and that is 5.5. So FG is my apothem, okay, and it is 5.5. Okay, the radius of the polygon is 6.8. We already said those first 2 that we found were considered the radius. What if I ask you to find GE?
Four,
Okay, how'd you get there?
because AB is 8. And G bisects AE, and AE is congruent to AB.
Okay, yeah, that's good. AE is 8. Here's another way, and that would definitely be the easiest way to find it, okay? Because it's going to get bisected, right? And so we know it's going to be half. I also want to show you this. If I did the Pythagorean theorem here, because I have a right triangle, I could do x squared plus 5.5 squared equals 6.8 squared. Let's say I didn't know this piece right here, but I knew both of these, then I could do the Pythagorean theorem there. Pythagorean theorem is still going to be in play today. I even used over and over and over again. If I have a 15-sided figure, I'm not going to draw a 15-sided figure. No thank you, right? But if I had a 15-sided figure, what would be the measure of one angle inside of that? Think about this picture right here. When I had 5 sides, I had 5 angles, so I divided by 5. So if I have a 15-sided figure, what am I going to do? Divide by 15. The first one we divided by 5, yes. Okay. So we just take 360 divided by 15, and that gives me 24 degrees. Okay. Every angle on the inside of that would be equal, because it's regular, and each one of them would be 24 degrees. All right, so here we have a square, okay? And what we know about a square, as I told you before, we know some regular polygons, right? Equilateral triangle, a square. A square. It doesn't just come right out and tell me that it's that it's a regular quadrilateral, but what I know about a square is all 4 sides and all 4 angles are the same, okay? So for instance, I know that YZ, XW, WZ, and XY are all the same. Okay, 4 equal sides. We also know that we have 4 right angles because we know a square has 4 equal sides and 4 equal angles. So it is a regular polygon. It just didn't come out and use the word regular here. Okay, the center. The center is what? When I name a center, what am I going to use? How do I name a center? Yeah, just the one in the middle, right? The center is a point, point P. Point P is the center. It's the center of the circle. It's also the center of the square. So it's the center of both. If you're wondering, what are we asking for the center of? We're wanting the center of both. Okay, the radius. The radius, once again, is also the radius of the circle. It's also the radius of the polygon. It connects the center to a vertex, right? So PY, I could do PX, I could do PW. I'm just going to label the 2 that are already drawn in. PY or PX. Both of those are radii. Okay, the apothem. Right now there's only one apothem drawn in. The one apothem that's drawn in is PQ. If I wanted to do this one, then I would just need another letter there, right? If I put an R or something right here, I could call it PR. But we don't have a letter there, so PQ would be the only one that's already drawn in. Okay, a central angle would be an angle at the center, okay? We got several of them here. But the most important thing, when you name a center, what letter has to be in the middle? The center, right? P. P has to be in the middle. So I could say angle XPY. I could say angle QPY. The important thing is that P must be in the center. Okay? XPY is probably the best because Q doesn't go all the way to the edge of the circle, but that's okay. It's still at the center, it's still at P, so it would still work. But XPY is probably the best in that case. Okay, once again, same picture, different questions here. We're looking for the measure of some angles here. So when I do these, what I like to do is draw the big triangle first, okay? And I want to know what the measure of this little angle inside here is going to be. Well, if I have a square, how many central angles would I have inside of a square? 4, right? 4 sides, 4 angles, right? Same thing. A second ago we did one with 5. This one has 4. So to find this angle right here, we're going to take 360 divided by 4. Which is 90 degrees. Okay, so I'm just going ahead and mark it with a right angle because we know it's 90 degrees. We know it's a right angle. Okay, then I'm going to draw in my apothem. Okay, the apothem is going to separate XY in half, and it's also going to be perpendicular to it. When that happens, measure of angle XPQ is going to be half of 90. Because we're talking about X to P to Q. We know the big angle is 90. I'm splitting it in half. Okay, the last one is angle PXQ. Okay, this angle right here, we know this one's 90. We know this one here is 45. So I could take 180 minus 90 minus 45. Okay, so guess what? We have a 45, 45, 90 triangle. That might lead us into some fun for tomorrow because guess what we might get to use again? So we talked about a 45, 45, 90 triangle before this semester. Good times, right? Remember when I told you to hang on to those triangles that we made? We're going to use them again. Might want to bring those with you tomorrow. If you haven't located those for a while, you might want to bring those out tomorrow. We're going to use 45, 45, 90s and 30, 60, 90s. Okay? So we're going to see some of those tomorrow. I know. You guys won't be able to sleep tonight. So excited to be able to use those again, right?